Thank you, everyone. Thanks for joining. This is an exciting meetup. It's actually our last meetup on the TensorFlow and Practice Specialization, covering course 4, week 3 and 4. And we started this journey last time where we talked about forecasting using statistical approaches and a simple deep neural network performing forecasting. And we saw some different loss functions and different behaviors. And sometimes the summary was that sometimes maybe it's better to try a simpler or a more classical statistical approach compared to deep learning, see if that works well compared to a deep learning approach. And if from a forecasting perspective, if you're only interested in the gap between what your model is outputting and what is the actual value, in this case a regression problem, then maybe a simpler classical approach would be appropriate. Today we're going to use some more tools from our toolbox. We noticed that actually time series, they're inherently dependent on time, so the order of the values matters. And when I hear that, that brings me to mind recurrent neural networks. So this week we're going to talk about recurrent neural networks and convolutional 1D to use them to actually perform forecasting in this deep learning approach. And next week on July 3rd, we actually have the honor to have Lawrence Moroney, the AI lead at Google folks, who also created the course with Andrew on the very course that we're taking. We're lucky enough to have him. I contacted him. He's a very nice person, big fan of his. He'll be able to join us and share some feedback with us. We're going to share some feedback with him. We're going to ask him some questions. And a very open discussion. So if you have any questions, any feedback for the course or for Lawrence specifically, think about it and join us on July 3rd, right before Independence Day. Then after that, I'm still putting this material together for some tips on how to prepare and pass the TensorFlow Developer Certificate. It has two components to it. It has one that's obviously dependent on the content, but also another component that's dependent on the hardware you need and how to set it up so that within the limit allowed, within the 5 hours that the exam is, you can make most of it and pass the exam. Cool. With that said, let's start with week 3 of course 4, and I'll have Robert lead week 3, and I'll pick up from week 4.
Okay, as George has already introduced, we're working through course 4 of the TensorFlow and Practice Specialization. This course is on sequences, time series, and prediction. And we'll be starting with week 3 this week, which is recurrent neural networks for time series. So this is a picture of the network we're going to be looking at here. It's going to have 2 recurrent layers from the input. We always read these things from the bottom. The input is down there where the X is. I think I have a mouse I can move around as a pointer. And we have recurrent layer number 1, recurrent layer number 2. We'll have a dense layer, and we're going to be producing forecasts in the top. And just as a reminder, this week, or this course rather, we are doing regression modeling, which is a change from the first 3 courses where we were doing classification modeling. And as another reminder, there are a variety of different types of sequence models that are in use in deep learning. So one-to-one really isn't a sequence model. That's this first one here. One-to-many is you have one thing as an input and somehow you're generating a sequence. So an example of that might be an image captioning process where you have an image, you feed it through a convnet, and then you just get this matrix of features here, and you want to produce a sentence. So you're going to do this in a recurrent neural network model where each of these time steps is predicting the next word of the sentence. There are also the opposite, many-to-one, where you start with a time series and you're predicting a single output. And the classic example of this is sentiment classification. So we've done this back in course 3 as well. We had a sentence and you want to predict whether it's a positive or negative sentiment about a movie, and that output is just a single binary value where the input was a sequence. We also have many-to-many models, and there's two different versions of those many-to-many. One is a many-to-many that does not require the output sequence to be the same length as the input sequence. Here we have an input sequence that is all going into a recurrent neural network, and at some point here, the input sequence has been encoded, and then we're decoding it into an output sequence. The classic example of this is machine translation, where you might start with a sentence in French that is any number of words and translating it into English that is not necessarily the same number of words. And finally, the many-to-many recurrent neural network. This is where we have a sequence and we're predicting a single output that corresponds to each of the elements in the input sequence. And a good example of this is part of speech tagging or named entity recognition. If you want to know what part of speech each word in the sentence is, noun, verb, adjective, then you can run a neural network to classify that in this way, and you use this type of architecture for that. So the model that we will be using for this week is the sequence to vector. And in this case, we have X matrices coming in, and we'll talk about the dimensions in a bit, but we are feeding this into a first cell of this unrolled neural network. Remember that each of these cells, although we're seeing them multiple times here, it's really just one cell that all has the same weights. And in this particular case, there's just going to be 3 neurons in this cell. And that cell in a simple neural network is just going to output a vector h, and that will be the same vector that is the vector y here. Now, in this one, we're looking at a many-to-one, so we're only going to actually look at the final output. But we also have the option of setting the parameter return sequences equals true, and at that point, we can output many, and now we're outputting all of these y's, one at each step. So let's talk a little bit about the shape of the input and the different steps in this process. So what's pictured down here is batch size and series dimensionality. Batch size, of course, is just a number of samples that you choose to process together. In this case, we're going to send them in batches of 4 to the neural network. And on this axis, we also have time steps. So batch size is the first dimension. Time steps is the second dimension, 0, 1, 2, 3, all the way up to 29. And the dimensionality of your series, which in this case is univariate. And what that means is that we're only looking at one quantity or one different type of measurement going in. That's not necessarily always going to be the case. And maybe a good analogy is to think back to what we did for the NLP models that we looked at in course 3. And this was one of the visualizations that we looked at back then. This is from the Iran University of Science and Technology, a way of visualizing the input in an NLP model. So we have a number of sentences that we are feeding to the neural network, and the batch is the number of sentences. The time steps is, say, the number of words that we're feeding each time. Suppose we're doing, well, we have this recurrent layer showing here, but let's assume we have a dense layer on the top that isn't returning sequences. So we're doing some kind of sentiment classification here. So each element in the batch is a sentence, and that sentence has a number of time steps in this direction. But we also have another dimension going this way, which corresponds to the word embedding. So typically we had 64 or 256 or 300 dimensional word embedding. So please feel free. I see that someone has raised a hand. This is a small enough group. Please feel free to unmute yourselves and ask a question as you wish.
Hi, I'm audible?
Yes. Hi. Is it Jyoti?
Yeah, hi, Jyoti this side, yeah. So basically in that image, when it was given memory cell and we told that it's flattened, okay. So if in that case, do you feel that this is only one memory cell and I am passing x0, after that x1, after that x2 sequentially into one memory cell, or it's a multiple memory cell?
So if I understood the question, there's actually different ways of thinking about it. It's really one cell, but we are visualizing it in a way that is unrolled. So what I mean by one cell is that there's only one set of neural network weights that are to be trained. So in this particular example, the batch size of 4 is not going to impact your weights. You're really just training a 3x1. Or you have 3 neurons here, and 1 is your univariate dimension coming in here. So you're just training 3 neurons, but you're retraining those same 3 parameters or 4 parameters with a bias at every one of these steps. So when you do back propagation through time and you calculate the gradients, you're updating the weights separately at each one of these steps, but it's the same weights that you're updating.
Okay, in that case, these 3 neurons are there in the memory cell, and when I'm passing x0, then that's getting updated with a value. Again, when we are passing x1, that same 3 values will be getting updated again.
Can you repeat? I didn't follow that.
Okay, so that means in the memory cell, I have an 3 neurons are there. Okay, and when I am passing x0, means one batch, these 3 neurons are getting updated. Okay, then once again when I am passing x1, then again same 3 neurons are getting updated on that part.
Yeah, now if you're going in that direction, what you're describing is forward propagation, right? So the neurons are getting computed in the forward propagation sense. The weights are not being updated.
Yeah. Okay, yeah.
The weights will be updated as you go backwards this way.
Yeah, but every time we are just touching that same 3 neurons only, not for x0, another 3 1, it's not multiple, only that in the network we have 3 neurons only.
That's right. A lot of times you'll see these things drawn in a rolled up fashion to highlight that fact. I don't think we have one of those in the slide deck at the moment, but we can certainly, I'm sure someone can post a visualization like that to the chat, and we can come back to that if you wish.
In that case, we can think of it's always working in a sequentially. It's not working in a parallelly. If I have a huge data, then it will take a lot of time to process that one.
Yeah, that is correct. So recurrent neural networks, Jyoti, by definition, are sequential. You cannot run separate parts of it in parallel. You have to run them sequentially. And actually, we have an NLP tutorial a couple of weeks ago. We have the recording on YouTube. I recommend you check it out. There's 2 or 3 sessions that go into more detail of how recurrent neural networks work and what exactly happens during the forward propagation that Robert explained, and also during the backward propagation, or the back propagation when the weights are actually updated. There are 2 different phases of this process.
But the fact that it is necessarily a sequential process does limit the amount of parallelization that can be done with this type of design.
Okay.
Yeah.
Yeah. Thank you.
Good question. Thank you.
Sure. Mm-hmm.
Yeah.
So let's see. So what I was hoping to do with the NLP example was draw an analogy between the way we have to instantiate our neural network for text-based models and the numerical data that we're looking at here. So what you can think of as the equivalent of a word embedding is the series dimensionality could be multivariate. So for instance, perhaps we have a data set of weather data, and these W's here that were word embeddings being fed at each one of these batches, perhaps they are weather embeddings, so to speak, and one of the dimensions is the temperature, another dimension is precipitation, dew point, things like that. So what we have is a three-dimensional tensor that ends up being passed into this memory cell. 3 dimensions of batch size, number of time steps, and the series dimensionality, which doesn't have to be univariate, but will be for our examples for the rest of this course.
So Robert, you want to talk a little bit about the output size, since you're talking about the input size as well? Or the output size?
Yeah, that's a good thing to do. So the output here, of course we have the batch size is still present in the output, and the number of units, 3, is the size of your memory cell. So in this case we had 3 neurons, not shown here, in the memory cell. And then the dimensionality here has been removed. So in the case of the word embeddings, you've turned that into some other type of feature. But you still have the time steps in this dimension. So I believe that the Keras tensors are stored with batch size, by time steps, by number of units.
Yep.
But it's going to be a 3-dimensional tensor again at this level.
Awesome. Thank you.
Mm-hmm. So for the structure of this neural network, we're looking at this thing unrolled again, and we're going to have 2 simple recurrent neural network layers here. And simple recurrent neural network means that the quantity in this arrow is the same as the quantity in this arrow, and that the cell, there's none of the complications that we'll see in the LSTM type cells. And note that we have return sequences equals true, and we don't have a return sequences equals true argument for the second recurrent neural network. What would happen if we did that is that the second one would also return sequences. So you'd see something like this, and now all of a sudden you've got the dense layer has to be replicated. And Keras can do this too. And if you do that, it'll end up using the same dense layer, dense network here. So you get the same weights at every one of these time steps. So you could do this if you want to predict a sequence coming out. But for our problem here, we're going to be forecasting just a single number. So we're going to use just a single output there. So we want to use return sequences equals false, which is the default for the second RNN. So another thing I wanted to mention here is the input shape. That looks a little bit different than what we just discussed. We had a batch size and a number of time steps and a number of quantities in the time series, your embedding dimension, so to speak. So Keras, or TensorFlow rather, is always assumes that there's a batch size out front, so you never have to pass that as part of your input shape. Then the none in the next quantity here, it refers to the time series. And what that tells TensorFlow is that that time series can be any length. This is the beauty of having a recurrent neural network that uses the same parameters at every step, is it's very easy to scale the network up and down depending on the length of your sentence. It doesn't matter. You have the same weights, you're training it the exact same way. It just takes a little longer if you have a longer time series. And the 1 at the end is the univariate, the fact that it's a univariate time series. And because simple RNNs always expect there to be a third dimension in that tensor, even though our original time series don't have an extra dimension because they're univariate, we have to put that here. Another thing to note on this particular network is that the final layer is a dense 1 with no other parameters. So what that tells us is we have 1 neuron here. So we're going to take the output of here and run some kind of a linear transformation on it. We have a single weight on this thing here, a bias for each. Well, this thing here is actually a vector, but it's still, you're only going to be producing 1 output. And the fact that there is no comma activation equals something means that we're using the default activation, which in the case of a dense layer, the default activation is linear. So this is actually just a linear function in this final layer. So another thing that we experienced for the first time this week is lambda layers. And Lawrence presents these rather enthusiastically. He's happy to be able to do transformations within the model definition that really make things easier as far as passing data and working with, you don't have to pre-process your data before feeding it into the model. You can do some of that pre-processing here. So what are the lambda layers that we're looking at here? There's 2 of them. We have a lambda layer on the top, which is TensorFlow.expand dims. And so this is actually doing that pre-processing that we alluded to a bit previously, where we had to have that third dimension in the univariate time series, even though it's just a unit dimension. So what this is doing is it's automatically saying, give me a time series in that doesn't have that extra dimension and add that extra dimension to it. And so now the input shape to this function does not need to have none comma 1. It is just none, a straight none for the length of the time series. The other lambda layer at the bottom here is also interesting. And this is obviously a simple computation. He's just multiplying it by 100. And so you could ask, well, why would you do that? And the answer is that neural networks tend to operate in a region of numbers that, you typically want your values to be between -1 and 1-ish. And the weight initializations are constructed, the standards for that are typically constructed in a way that is optimized for processing numbers in those regions. Yet we know that for the time series that we are going to be predicting here, which I haven't introduced yet, we want values that are on the order of 100 or go up to 100. We want that capability. So yes, your network could start out with small parameters here and learn that it has to make big weights, but it's a little bit easier if you just kind of give it that initial multiplication immediately. So that's all we're doing here.
So it's interesting. So there's a difference here between like the lambda layer and the lambda functions, right? I mean, you do see the small lambda used a lot and very usefully when you're handling data. Mm-hmm. I think the big layers lambda to me is a bit of useful when you have toy systems, because the reason I say that is because it's going to be happening, like for instance, the pre-processing part at the top is going to happen every epoch. It's going to go back to your data and pre-process it over and over and over and over again. Mm-hmm. And that's not really realistic when you're dealing with a huge data set or maybe like a real world data set. The same thing at the end. It's a lot easier just to do that scaling back of your results one time instead of at the end of every epoch.
I suppose you could make that decision also based on how much time you expect to train versus inference. Because if your data is coming at you in a format that requires this kind of transformation in the field doing inference, maybe it's worth the training inefficiency to have faster inference.
100% true. Yep, agreed. You could also see maybe you're using a pre-trained model and you're not doing fine tuning on it. You're just taking it as is and using it. Then it's right. Very useful.
Yefim had a question. Yefim, go ahead and ask it. Go for it. Just unmute yourself.
Yeah, it's a bit noisy here. That's why I was typing.
Okay, no problem. I can read it for you.
No, that's fine. So what do we want to scale the numbers to different range? Not between -1 and 1, but between, say, -1,000 and 1,000 consistently. Would we have to worry about the loss of precision a bit less? Just pick a range and make it consistent. Or some math breaks down if we do not keep the values between -1 and 1. That's the question.
So I think you're asking a fairly general question about neural networks, and the answer that I would give to that is that when you look at the most classical activation functions, the sigmoid and the tanh, you typically have they're flat in some region of space. I suppose if I want the positive values to be, I need to be pointing that way in the positive x direction. So you might have them be flat around the near the origin, but then it levels off at a certain point.
That's just at the output layer, right? My question was about the weights, right?
Well, I think the reason I talked about the activation function there is that you want to be operating on a scale so that you are utilizing the curvature, but not so much that you're out here in the tails and unable to, and you end up with vanishing gradients.
Right, so the output is clear, right? The way sigmoid function works. The question is whether the weights are also kept in that range between -1 and 1. And so the question was, if you kept them from the starting point between -1,000 and 1,000, would you have to worry less about what vanishing gradient, right? You see what I'm asking?
So if you keep the weights, that means you're actually controlling the weight update procedure, and
you just pick the range that is not between -1 and 1, but between -x and +x.
Sure, but you don't really get to control the weights directly. I mean, you can put limits on them. You can do something called L1 or L2 regularization and looking at the norm, or you can clip the norm of the weights, but you don't really specify that I want my network to limit my weights between -x and x. That's the job of the optimizer, like stochastic.
Right. So during the computation, if the weight exceeds 1, are you clipping it at 1?
No,
letting it exceed 1.
I believe you can clip them, but we're not.
Yeah.
Okay, that's fine.
Yeah. That's more of a hybrid approach. This is more of a standard deep neural network approach where you let the optimizer update your weights. But you're recommending FMA is more of like a hybrid approach where you actually are involved in the weight update process.
Well, I was trying to find out whether for this one the weights are within a particular bound or not, or whether they are like floating point numbers for each, and it could be minus, millions plus millions, or whether they are between, -1 and 1.
Mm-hmm. Yeah.
Do you know the answer to that?
Yeah.
It's just like similarly when we have input values that are within a very wide broad range, we want to take a log or normalize it to within consistent range so that we don't have the values out of whack, right, for each input. So that's what my question was, whether you get some benefit with respect to like training time or precision or accuracy or whatnot if you pick a different range. That's fine. We can proceed. Thank you.
Well, I think the other point that I wanted to make regarding that was that with many of the other activation functions like a ReLU, there really is no sense of scale anymore that the activation function itself defines. However, the entire ecosystem within which neural networks have developed is largely based on the design that we expect the weights to be within a certain range. This is why we have the initialization schemes like the Xavier, which are also operating under that assumption. So it becomes easier to just chain different types of tools together and work with things if everybody kind of plays to the same standards.
No, I understand. It's just a design question because, you know, there was a lot of evolution and the railroad didn't happen like 20 years ago, right? It's a relatively recent advancement and people were using a different function. So that's what I was trying to figure out, whether, you know, it would be a superior approach or someone tried it and said, no, there is really no benefit. You have to do it between -1 and 1. Or people have been using between -1 and 1 because it means like you can, you know, fit a lot more stuff into memory, for example, right? Or computations become a little bit cheaper. That's the question that I was asking.
Sure.
Or whether, you know, some math breaks down, so you have to normalize it to that range. That's all right. Thank you, guys.
Sure. Welcome.
Yeah, Jyoti this side. So if you look onto the lambda layer, there is no weight is associated with that layer, right?
That's correct. It's just a defined function.
Yeah, in that case, means it's like an just for convergence of that flow, it's just changing that x value, my data value, what is coming out of the dense layer.
I'm not sure I understood.
You're changing, yeah, when you're changing what is coming out of the very last dense layer, you're just scaling it up by 100 here. So you're just changing the scale of the output.
Yeah. So means basically we can put it's like an post processing, means just to get an convergence that value we are doing that, means we can put an optimizer or something like that. It's functioning like that one.
Yeah, we have an optimizer regardless if we use lambda or not. It's just that the value that we're going to present to our loss function will be x. If we don't use a lambda, it will be 100 times x if we use the lambda. So the optimizer will take a different step based on if this is scaled or unscaled.
Okay.
So it will help a little bit with convergence because depending on what time series we use and what values they take, like if they're in the hundreds or thousands, it might help the convergence a little bit better and faster.
Okay. Yeah.
Welcome. Any other questions? Great questions. Yeah, please. This is an open session, so feel free to interrupt. Cool.
All right. So we also are testing out a new loss function this week that we haven't seen before in the course. This is the Huber loss function. And this loss function is defined as a quadratic for small residuals. The residual in this case is y minus f of x. F being your prediction of f is your prediction and y is your observed value. So this is the residual, and this quadratic function of the residuals is the very familiar mean squared error. This is what is used in ordinary linear regression, ordinary least squares regression, and that is the loss function defined by the blue curve here. We also have a, but what we're actually defining here is a hybrid. So we're looking at an absolute value if we're in large residuals out here, and we are looking at a quadratic only in the inside. So it begs the question, why would one do this? And the reason that this is done is that if you use mean squared error as your loss function, then what you can have is a situation where outliers have an extraordinary impact on your model. The reason this happens is because if you have an outlier, that's going to be a residual that's way out here, and then your quadratic function has just grown to really high values. So the quadratic function is an unbiased estimator of the mean of the residuals, but as we know, large values can offset a mean by quite a bit, right? If you have one very big number and a bunch of small numbers, the average can be a somewhat large number and be nowhere near the median of the numbers. The orange curve here is the absolute value line, and that is an unbiased estimator of the median. And in multi-dimensions, it's called the geometric median, but it will essentially prefer to find the point in your data set which has the smallest sum of distances to all the points, not sum of squared distances. So that tends to be a little bit more robust to outliers that would otherwise impact your data substantially. So what this Huber function tries to do is just a mix. It says, well, we don't want to have large errors far outside the zone compromise our fits. However, it's really nice to have this convex function when you get close, because it's much easier to optimize a function when you have a gradient that is continuously changing as you approach this side. What will happen here and you think about just having the median of a univariate set of numbers, once you get between the two in the middle, then it's just a flat function. So you really can't find a global minimum. And so your optimizer will kind of bounce around a little bit between a few of them, and maybe it'll give up if you give it some kind of stopping criterion. So this is just a little bit of code here to produce this plot on the right, and we'll see this Huber loss function in the compilation step of our model. So this slide, we're going to go through how the code is built for this problem. So we start, again, we are using synthetic data only. So we have, and this particular code block, I believe, is out of order. The series is defined as a trend, which is a linear function. So we have a linear trend that's just growing with time. We have a seasonality, and I don't see that defined here, but it's a function that is periodic and kind of an arbitrary function that is periodic. We don't really care what it is. We're giving it a period of 365 here, which implies somehow that our time steps are probably days of the year. And we're also adding noise because we don't want to make this problem too easy. So now we're going to start to define our model. We're going to set a seed, and we have to do so in TensorFlow and in NumPy. And the reason we're setting the seed is to make sure that we can get consistent results so that we can understand what our model is doing and make sure that we're actually running the same code that we did the previous time. This first one, we're going to have the lambda layers that we saw previously to expand the dimension, add that univariate extra third dimension of the tensor. Simple RNN, returning sequence is true on the first one, but not on the second one. So we're just going to send a final output vector to this dense, which is a linear, and we'll multiply that linear by 100. So then we come to LR underscore schedule, and that is the learning rate scheduler. And we ran into that last week with, I think we were doing dense neural networks at that point.
Yep.
But we were feeding a different learning rate on each epoch. And in particular, we're going to grow the learning rate on each epoch, which is a little bit counterintuitive. We had a discussion on that last week. I encourage you to refer to that video. I think we thought about, why would one do that? But Lawrence does it more for academic purposes here, I think, just to say, well, let's see what learning rate might be a good one for this problem. So we start with a small learning rate, and eventually we start to find a minimum in the loss, and after a while, the larger learning rate starts to lead to jagged behavior. So we say, okay, let's pick a good one. So we say, well, it's 10 to the minus 6, 10 to the minus 5, somewhere down here. Well, let's pick a learning rate somewhere in between there. So then we have what appears to be a bug. There's a choice is made that the learning rate, in the video, I think Lawrence says that he wants to choose one that's about halfway between 10 to the minus 6 and 10 to the minus 5. But 5 times 10 to the minus 5, the one that is actually chosen and shown in the code, is this red line over here, because when you multiply 5 times the larger of the two values, you actually end up out of the range. So I think this was unintended, but it does make for an interesting case to see what happens when we run it with this suboptimal learning rate.
So the right value would be what, half 10 to the minus 5? 1/2?
Yeah, I actually tried another one later, and I chose 3 times 10 to the minus 6.
Okay.
Because to me this seems more like a logarithmic scale, and 3 is roughly halfway between 1 and 10 in a logarithmic sense.
Hi. Again, I stuck on that lambda layers only, because whenever we are going a normal implementation, deep learning, right? Then we have only one output layer. Then we used to stop there. How does this? If I'll not put this last keras lambda layer, how does it will affect my convergence, or how does it will affect my flow time series model? Is it barely necessity?
How does it detect what?
My normal flow. If I'll comment that one, then how does it matter to my accuracy or anything on that?
Oh, you're asking if you comment out the lambda layer, how
Right.
your accuracy change?
Yeah.
So I think in this case, the model is probably capable of eventually converging to a good solution, but it might take longer because our initialization process has started with weights that are probably too small to get the values that we need. So it's going to take our function a while to learn to increase those weights to the scale that we need. I believe that the inclusion of this lambda layer here is really just speeding up the training process. So if you're comparing after a set number of epochs, you might do a little better.
Okay. Okay. We'll check once. Yeah.
Sure. So is that everything I wanted to say about this slide?
So I just was going to point out, I played a little more with his method of choosing your learning rate.
Oh,
and it's also dependent on and at least for the stochastic gradient descent optimizer, it's dependent on that momentum setting also. Because that depends on like the prior values and how much you factor them into the change that the optimizer recommends. So, but he doesn't really go through how you optimize or choose the value for momentum. He's kind of randomly chose it.
He just leaves that as a constant, doesn't he?
Yeah, but that also can be. I assume you can do some kind of learning. You can't do the learning rate scheduler, but maybe you invent a new type of momentum scheduler to predict that. I don't know, but yeah,
the learning rate scheduler is built into Keras.
Yeah,
I assume that's a function that's used often. Perhaps there is no momentum scheduler.
There isn't, no. So far as I know, you could write your own callback, of course.
Sure.
So the moment you introduce a momentum, you're not using the classical SGD anymore where the learning rate is constant, right? You're using a hybrid SGD where you're using first order or second order momentums then? Is that what it is?
Say it again, George.
That second argument momentum, it basically introduces a new momentum-based optimizer compared to our non-momentum based.
Yes.
Got it.
I think it provides a little bit less jaggedness in the output.
Probably.
Yeah, I don't remember the last time. That's why. Good thing you brought it up.
Yeah, the Keras in the SGG in the API, they have the formulas that show where momentum is used in the learning rate. All that. Yeah, so it's basically what you said, George. It's just gonna introduce that and smooth it out.
Cool.
But momentum is exactly what it implies in the physical sense. If you've taken multiple steps in the same direction, you're not going to turn on a dime just because you see one training example that's in a different direction. It's gonna be somewhat of a weighted average of recent steps.
Exactly.
That's the idea.
It's like a snowball effect.
So we're going to compile this model with the Huber loss as we decided before. We're also going to check out the mean absolute error metric. We're going to output that, but we're going to train based on Huber loss. So this is what we get from this first attempt at RNN models. This is with the learning rate equals 5 times 10 to the minus 5, as we discussed before. So if you look at this fit, it's not great, right? There's definitely a bias here. If you look at the orange line, which I guess this is not labeled, so it would be helpful if it were, but the blue line is the original time series, or the blue line is the validation set, and the orange line is the forecast that our model is producing. So if you look throughout the time steps, we're under predicting pretty much everywhere, except maybe on this downturn here, we're not under predicting. We're doing pretty well there. We're under predicting over here, we're under predicting over here, but we're sorely under predicting here, where the model seems to be somewhat incapable of predicting a value higher than about 83. So we'll think about that a bit and investigate that. Our overall mean absolute error here is 6.8, which is surprisingly low considering how many values in here have mean absolute errors of 20 or so. Overall, 6.8, not too bad. I don't remember how that compares to the dense neural networks that we did last week. I think those were using this exact same data set. And I did
4.9 was pretty much the best we were getting.
Yeah.
4.9.
5-ish. Yeah. So this is doing significantly worse than that. We also produce a couple of plots here of the mean absolute error and the loss. First of all, we're looking at all of the epochs, and it's kind of difficult to see what's going on down here. It looks like we get to something that's kind of flat quickly. But now over here, we're bouncing around quite a bit. It's very jagged. The loss is tracking the mean absolute error quite highly, which suggests that of that Huber loss, more of it is in the linear side tail region than in the convex quadratic region. And I don't want to confuse people, these plots are labeled accuracy. And we had a discussion last week about how that word is not, we don't want to confuse that with the classification accuracy from tasks that we were doing in previous models. This, I think here just seems to be used more as a generic word that is not meant to be taken in any technical sense. We're looking at both the mean absolute error and the loss. So based on the issues with the that we discovered here with the learning rate being kind of out of scope, I decided to go back and rerun it with a learning rate that is in between the originals, 3 times 10 to the minus 6, just to see if we do any better than this 6.82. And we actually do a lot better. And now we get a mean absolute error of 5.8. We still see under prediction over here in time steps about 1250 and higher. It looks like we're not really biased though over in this region, and we're doing okay here. And the plateau is still a problem, but it's not quite as clipped as it was. It looks like it now gets up to 90 or so, which is definitely helping us with that mean absolute error. This function is again kind of difficult to see if you plot all epochs. So we come here and look at what's happening for just the large numbered epochs, and we can actually see that even after 400 epochs, it's moving around. It's still a little bit jagged, but there does seem to be still a downward trend. So possibly it would have been useful to continue training at this point. Maybe one could lower the learning rate to as you get lower, and maybe try to find a minimum a little easier. But it doesn't look like it's necessarily reached the optimum yet, but it's probably not too far away.
Any comments on the gap between the MA and the loss, or it just happened?
Comments on the gap between the MAE and the loss. Oh yeah. So in this case, now we have the MAE and the loss are still very much tracking each other if you look at these two functions. And the gap is almost exactly 0.5, which is also not surprising if you go back and look at this curve here, where we're really just plotting the loss function is the Huber loss, and the accuracy that we're outputting is this orange line here. And as long as we're not too close to the middle here with very small residuals, if anytime we're out here, we're going to have a constant offset between the accuracy and the loss. So, and it is exactly a half.
Nice.
So, and you can see that from the code here. If your little x is greater than 1, then you're really just taking the absolute value of x minus 0.5.
Nice.
So in this case, what that's telling us is that most of our points are in the linear region. And that's not really too surprising because our mean absolute error is still quite a bit higher than the size of that bowl. So this little visual here is a slight sidebar, but I have we've done a number of visualizations like this in the course where we've looked at the time series offset by 1. And in this case, we discussed it in the context of a naive forecast. If we're really using all the data up until today to predict tomorrow's stock price or tomorrow's temperature, how bad would we do if we just used the naive forecast and said, let's just use today's temperature to predict tomorrow's? So what we end up having here is a plot that looks like this if we use that kind of forecasting. And I don't know about the rest of you, but I tend to find this very difficult to interpret. Sometimes it's a bit of an optical illusion, right? It looks like it's a pretty good fit because the lines are right next to each other, right? They're going up right here, right next to each other, and it kind of belies the fact that, well, no, there's actually a point here that was predicted to be 70, but the actual output was 105. So it tends to obscure the quality of fit. So I thought I'd introduce an alternative way of visualizing where you're just looking at the time steps. So at this particular time step, what we wanted to predict was 105, but what we predicted was 70. So what if we just look at observed versus predicted? And this is a very standard way of looking at any kind of regression model output. This will help you to kind of visually assess the R-squared or goodness of fit for a linear model or a a regression model, any kind of least squares regression model can be assessed with an R-squared. And you can see that in this case, as we saw earlier, when we're in the range between 40 and 60 or even up to 70, we had decent fit. But for the highest values that we needed to predict, up here or down here, we're plateauing. We're unable to predict up here where the actual value is. We changed the learning rate, which sped up our learning and maybe improved things a bit, changed our plateau here, but we still have an inability to reach this value up here. So our fit is what you would call heteroscedastic, right? The variance or the errors are changing quite a bit depending on where you are in the.
Do you recall, was our training data, did it go up above 80?
That is an excellent question, and I'm going to address that in a bit.
Okay.
But
the extrapolation problem, right?
It's a what?
Extrapolation issue?
Exactly.
Okay.
It's an extrapolation issue.
Okay.
We had a trend in our data set. I don't know if there may be one image of it in here with the full. Yeah, this is actually a different data set.
Okay.
Built with a similar model where we had a trend plus a seasonality. Mm-hmm. And you can see that by slicing your data, choosing some kind of split point here, and using this as training and this is validation, what you're asking your model to do is to predict values higher than anything it's ever seen before.
Right.
And certain models do not do well with that. So we'll come back to that in a bit. Are there any other questions on this before I move into LSTMs?
This is great visualization, Robert. I like this.
Sure. So on this slide here, we're going to look and see, well, can we do a little better with an LSTM model? So we're going to define our series in the identical way. And because of our discussion with the seeds last week, this time when rerunning all of these models, I actually checked and made sure that I was getting the same time series for each bit, and I was. So that's not an issue here. So what we're going to change here is we're going to replace those simple recurrent neural network layers with a bidirectional LSTM. And each of the LSTMs will have 32 units in a cell. And the first one will return sequence as true. The second one will return sequence as false. So we'll be outputting a single vector again. And we've discussed LSTMs at length in previous weeks. And there are lots of great resources on those. So I don't really want to go into a ton of detail on it. But just as a reminder for everyone of how the LSTM differs from a simple RNN, they've got a lot more gates inside. And you've got different outputs. You've got both the standard output, but you've also got this cell state that is able to remember data for longer numbers of time steps. And that is something that we used back in sequence prediction when we wanted to remember the value from the beginning of a sentence, or back in NLP. So we'll be trying one of those models here with the time series. And the thinking behind that is that maybe we can train this kind of a model to learn something about seasonality, right? If the number of elements in our sequence that we're feeding into the model is actually large enough, we could, in theory, learn something about the seasonality and learn that, hey, we should be looking back 365 days, and that's about the shape that we should be looking for. In reality here, we are not actually feeding that data in. We're just looking at, what is the window size? 20 previous time steps. So the model has no information regarding what happened 365 days ago for any particular prediction. So again, we're going to do the learning rate scheduler trick. We're going to start with a small one, increase it, keep the momentum constant, same loss function, same accuracy, same everything. And this time we get a learning rate that drops a little bit smoother and down about 10 to the minus 5, and then it starts to get a little bit jagged. So we'll pick a learning rate of 1 times 10 to the minus 5. This time the minimum in the curve is what we'll work with the first time this time. And here are the results. So what's interesting here is that we really seem to be more biased than we were previously, actually, on some of these flat regions. The LSTM model is significantly under-predicting on these flat lines. It's doing okay here. It's also plateauing, not quite as bad as our high learning rate model was originally, but it's doing a roughly equivalent to the lower learning rate model here. And that's going to lead to a worse MAE overall, almost 7. We see that the MAE and loss functions they drop very quickly again, but they're kind of steady here, and they're tracking each other almost perfectly. So we again, maybe it's declining here a bit, but because of the jaggedness, it's really difficult to tell whether it would be an improvement to train longer. It's probably not. So at this point, the 3rd week ends for course material, but I know that George and I, and perhaps some of you, did a number of experiments as well. So first of all, one thing that you might try is just changing the design of your neural network. So replace that bidirectional LSTM with a single directional LSTM. And we get worse performance here. It goes to 7.3. Another thing you could try is bidirectional 3 layers, 7.21. Similar looking results.
Like we're throwing money at the problem.
What was that?
Like we're throwing money at the problem.
Yeah, exactly.
By money, I mean computation resources.
Throwing computing power. You're throwing away all your possible bitcoins you could be mining on this problem. So this particular one, did you want to say a couple words about this example, George?
Yeah, this was just a different example, but basically same comments that you made, Robert, about the previous time series, and just similar approach. This is just looking at it for a slightly different time series.
Right, different time series with a lowered noise level.
Yeah.
And these are the results for this different time series.
Yeah.
And it's the exercise at the end of the week, so you want to make sure that you could get a result less than 4. It looks like we succeeded at that.
Mm-hmm.
The difference here, I guess the biggest thing of note here is is this particular function. Did you want to say anything about that?
Yeah, so don't remember, did we use the Huber loss and the MAE?
Yes.
Yeah, so I think it's the comment that you made again before, but then again, this gap here is not 0.5, so.
Right, and I
then try to
think
interpret this gap.
the mean absolute error. I suppose if you go back and look at the other curve, it doesn't look like the mean should ever be higher than 0.5, does it?
Yeah, it looks pretty steady, but then again, the values are so small. I just don't know if there's actually a trend here or there's like a constant that separates these two time series. And where is that constant coming from? Is it from the nature of the time series?
This
gap.
So there's a constant that separates what?
The MAE and the loss function. Where is that gap coming from? Is it from the nature of the time series? That's my only assumption. Like, because our network is more or less the same as before. The only difference is the input data, right? The input data that we've fed into this network.
Right. So certainly, since the fit is better here, I would think that you're more likely in that quadratic region where it's convex.
Mm-hmm.
But if these means are being calculated correctly, you wouldn't think that the mean absolute error and the loss would ever be more than 0.5 away from each other.
Yeah.
So I'm a little bit confused by this.
Yeah, I'll take a look. Yeah.
Yeah. But yeah, it's an interesting question. So I did different investigations on this same data. And what I was most interested in was this plateau. And I went back and I looked at the model here, and I'm trying to think, well, why is it that we can't extrapolate? And if you think about machine learning in a general sense, there are many times where it is dangerous to extrapolate, right? There are typically no reasons to expect that trends will continue indefinitely or that trends will continue at all. There's a reason that the phrase regression to the mean is a thing. So it makes sense that many models are hesitant to extrapolate. However, we've been given a toy problem where we know the answers and we know that we want it to extrapolate. So I tried to figure out, well, how could we get it to extrapolate? And one thing that I zeroed in on was the activation functions that we're using. So in the original models, we were using an RNN, simple RNN. And if you go back and look at the TensorFlow documentation, the default activation for a simple RNN is tanh. And that's the one we were using because we didn't specify an activation function in our neural networks. And if you think about the tanh function, what's it going to do? Well, it has a somewhat linear region here, but it asymptotes to 1 on one end. It goes to -1 on the other end. And when you feed it a bunch of training data, the neural network is going to be moving these weights around, trying to take advantage of this nonlinearity somehow. And it's going to want to peg some of these values up here. It's going to want probably most of them to be in the middle, but you're going to have some values up here. And what you're going to end up with is, if you send that network at inference time, send it more extreme values, it's not really going to be able to predict more extreme outputs because it's stuck here on this tanh, which has a maximum of unity. So I thought it would be interesting to investigate other activation functions. So one thing I should note is that the dense, remember we fed these simple RNNs to a dense layer going out. So there is still another linear layer at the end. So, and then we're doing a lambda function on that as well, multiplying it by 100. So we can certainly get numbers up to 100 and more from this network on its own. But if it hasn't been trained with numbers out there, it may be pegged at whatever it's been trained on. So I tried to play with the activation function and tried 4 different ones, the tanh being the one here in the upper left, and looked at the fits, and it looks like I intended but forgot to actually put the MAEs on this slide. So I can go back and do that after the talk, but the tanh MAE was 5.67, almost 5.7. And interestingly, Relu had a similar one, also about 5.7. And Relu also failed to overcome this plateau. However, replacing that last RNN activation with a linear activation, basically the lack of activation at all, or a leaky Relu, both of those managed to do much better at approximating this plateau. And they didn't really seem to improve the bias in the flat regions. We still seem to underpredict in a lot of these points. And our MAEs for those two were about 5.4. So in both cases, we're not doing as well as we did in the examples in the previous course with a dense network that was looking at the problem.
Nice, interesting.
And just to get a sense of where we are in the training process, I cut each of these off at 400 epochs, but it doesn't seem like any of them were quite done optimizing yet at that point. There's definitely still a downward trend on all of them. In some cases, you can clearly see the gap of 0.5 between the, actually, it looks like in all 4 cases, honestly. You can see that you're in that linear region just about everywhere. So that was a lot of stuff on week 3. I hope it was helpful, but we can move along. If there are no questions on week 3, we can move along to week 4.
Yeah, are there any questions on week 3 before we move to week 4, if you don't mind?
I haven't been monitoring the chat.
Like we're good.
Okay.
Cool. Question? Awesome. Yep, thanks for looking under the hood.
All right, so let me stop sharing and give it back to you.
Great, thank you. Perfect. So week 4, which is the last week of the course and also the last week of the specialization, is utilizing all the different new concepts we learned, all the different tool sets we used, deep neural networks, recurrent neural networks, and actually using them in a real world time series. And before we start with that, I just wanted to remind us of some new layers, or some relatively new layers that we will be using, and one of them is a convolutional 1D layer. And if you think of it from a high level perspective, is that it's a generalization of the 2D convolutional operation, where instead of images, there are 2-dimensional and a filter or a kernel that reads for our features and scans our image from left to right and top to bottom. Now we basically have a time series, which is basically a collection of numbers, a sequence of numbers. Our filter is 1-dimensional as well. It could be different units, it could be a different size. We can specify that in the option here under kernel size. And what it will do is it will apply multiplication of the time series with that kernel. It will apply based on the activation, some kind of activation, and it will output a number. So it's the simplest way to think about it is a generalization of the, or simplification of the 2D convolution to the 1D case. And it takes similar inputs as other convolution operation. It takes number of filters, meaning how many times you want to do this operation. Think of it as parallel scannings or parallel operations. The kernel size, how many units you want to read at a time, so how big is your kernel. Strides, if you want to skip, or if you want to move 2 units of time at a time, or 1. Different padding operations when you start from the beginning of a time series or when you go to the end. In order for this operation to make sense, you might have to pad your data. And there are different padding options, as we've seen in other cases. Some other options, channels last, channels first, that's mainly used in image setup, where you have to specify how your data is structured, if it's width, height, channel, or some other combinations. There's something called dilation rate, which we'll see later, and activation that I use, and bias. There are some other functions that we're not going to use by default, but this is just a documentation I thought it would be a nice refresh opportunity for us. And in terms of shapes, it takes as input a 3D tensor. It takes batch size. How many examples are we considering at a time? Steps, how many steps of time we're looking at, and what is the input dimension. So if this is a univariate time series, this would be 1. This is a higher one, like Robert mentioned before, this would be a higher number. And what it will output is the exact same batch size, that won't change. New steps depending on if we use strides or padding. And this filter parameter here, how many times did we actually perform this operation in parallel? So if we do it 3 times, 5 times, we're going to get that many as a third dimension. Another parameter that we'll be using is called causal padding. And I want to take a view here, but basically what that means is that when we're trying to predict a future value based on a number of previous values. And so in blue here we have, let's say, the input, and in orange we have the output. So let's take this orange output here. It depends on 2 previous inputs, let's say time step 1 and time step 2. The one right before it, it only accepts 1 output, and the one right before it doesn't have, so it only accepts 1 input, and the one before it doesn't have any input at all. And the way they were constructed was that if we don't do any padding, there's no way for us to calculate correctly this predicted value at the very first initial phase. There's no way to accurately predict it. If we apply some kind of padding, this value here, this predicted value here, would be dependent on the padding, which is technically not real data. So the value of this output, it's meaningless to us. It's completely depending on whatever values we use. So meaning, so that's a suggestion that maybe we shouldn't even use this predicted value at time step 1. The predicted value at time step 2 depends on real data at this time step, but also from the padded value at this time step. So there's some partial information here, and I'm not sure there's an option to use this or not, but I think by default you will use this hybrid data and it will actually calculate this predicted value. And then going forward, the next predicted value is actually dependent on the previous 2 predicted values. So going forward, you don't have to worry about padding. So as I mentioned, this one depends on the padding. So if you're padding, let's say 0 padded, then whatever operation you do here, you're not really calculating any meaningful information, so you should ignore it. Another concept that I think is interesting is, or the same concept but explained slightly differently, is, maybe I didn't mention this, but another way to think of this is when we predict a value at time step t, we do not want to look at future values. So by default, prediction means that we're only looking at previous values. So you won't see any arrows from right to left. You'll only see arrows from left to right, meaning we look at past historical information and we generate an output.
I was actually a little bit, I had to do a double take when I was looking at the bidirectional LSTMs to think about, because at first I was concerned that they were violating causality. but you're actually feeding them time steps that were before the one you're trying to predict. You're just running backwards through those time steps.
Yes, yes. Yeah, your training set, your training set is, let's say, 1 to 100, and you're trying to predict 101st. You can read it from left to right, you can read it from right to left. Same in NLP in sentence when we're doing sentiment analysis. You can read it from right to left to right or right to left.
Right.
This is just the same, similar information, just that you won't see any arrows from right to left, that basically we're not violating causality, like you said, Robert. And the other concept I wanted to briefly mention was dilated convolution, where our kernel is not sliding over all our inputs. It's actually skipping some inputs. And this diagram might not be the easiest to understand, but I find that the 2D version of it easier to understand, where this paper here introduced the dilated convolutions, where instead of looking at patches of our input that are next to each other, like in dark blue here, we're actually diluting it. We're applying our kernel to a more socially distant version of it. So I guess this is the COVID-19 convolution version. You see our input is it's far from each other. And when we're applying to our kernel, we're actually looking at different values that are not next to each other. And there's a rate where you can specify how far or how close you want this diluted convolution to operate on.
On another COVID-related note, when you first changed over to your first slide, I saw conv1d and read it as COVID.
Interesting. we predicted it back then. No. Now let's find it here.
Our minds are distracted. Yeah.
I think we're overfitting here. Cool. So with that information, I think this slide just goes through another synthetic data, just using the conv1d layer with 32 filters, meaning 32 parallel operations. The kernel size is 5. We'll look at a window of 5 time units at a time. Stride 1, we'll look at it sequentially. We won't skip anything. Causal padding and ReLU activation. And the input shape, as you mentioned, Robert, the batch size is by default ignored. The second argument is how many time series our input could be, and could be of any length. And it's a unique value time series. That's why a third dimension is 1. Then the output of this conv1d, we feed it to a bidirectional STM with 32 units. We're going to return a sequence. A second layer of bidirectional LSTM, 32 units with our own weights. We will return a sequence as well. So right now, this dense one will take a whole sequence as input, and it will output just 1 unit. That we feed it to a lambda that is scaled out to a specific value, and I think this is judged based on the scale that we look at our synthetic data. So if our synthetic data range is between, let's say, -x and x, like you mentioned before, somebody, then this would be an appropriate version to scale it out, this number. We use a learning rate scheduler, the same Huber laws, so everything is almost the same except for this new layer, and we just want to see how our network operates. We have about 41,000 parameters. Most of them are in the bidirectional STM layers. We find the lowest loss. We find the learning rate for the lowest loss, about 10 to the -5. Plug that in. We also simplify our network a bit. We remove the bidirectionality. I saw that quite a few times. Not sure what the reason might be, but I guess just to see if a simpler network might actually give us slightly better results. So now we have 16,000 parameters from 41,000 due to the reduction of bidirectionality. We actually cut in half our LSTM layers. We fit it for 500 epochs. We do the forecasting. We are interested only in the specific time frame that we're trying to predict. And if we overlay it, it looks like we're doing a better job at trying to reach those high values that we had a hard time before. So you see we're actually close to 100 here, when the actual values are about 110, 115. And the MAE is actually 5, so it's a little bit lower, which is good. The lower the better than what we saw before. And if we look at our charts, there is progress being made, a little bit slowly, but there's still a little bit progress being made. And you can see that here. And you can also see that 0.5 gap that you mentioned, Robert. That's interesting to see.
One thing that I neglected to clarify earlier is that these plots that we're making on the right side of the screen here are for training data. And this curve on the left side is for validation data. So you have a MAE over here on the right that's on the order of 4.4 and an MAE for the validation that's on the order of 5.
Yep.
Just wanted to draw that distinction.
Awesome. Cool. So let's actually introduce a real-world time series that we used in this last week, and Lawrence introduced this data set, sunspot data set, which has a lot of data, relatively. It has data all the way from 1749 to July 2018. I have a sample here of how it looks. And for each month, it has the average number of sunspots. And those are temporary phenomena. If you come from an astronomy background, this might make more sense to you, but basically has to do with the magnetic field of the sun. And over time, you see these sunspots, which to us look darker, but they're actually of a really high degree of temperature. But compared to neighborhood regions, they're actually a little bit lower in temperature from my understanding. And also has to do with the magnetic field of how the heat is being dissipated, how particles are being dissipated in that region. So scientists have been monitoring these numbers all the way from 1749 with telescopes and giving us estimates of their average monthly number. And this is our time series. We have an index, which is the record number, the date, and the metric we're trying to predict. There are some discussions if there's any seasonality here, and there's some discussions. There's actually an 11-year solar cycle or a 22-year. I don't think the course settled on any of it, but I just wanted to point that out. Now, if we plot it, this data set has about 10, 11 years, given that 365 data points is actually. No, this is not daily. I take that back. This is monthly. So 3,000 months, I guess, is.
I think the data set started in 1749, and it's until somewhat recently.
Until July 2018. So yeah, so 300.
270 years or so.
Yeah. So so each data point is a month here. It's at the level of the month, and the y-axis is the average number of sunspots that scientists noticed. Then to actually do some prediction, we're going to use our different tool sets, our different toolkits that we learned. We're going to use a simpler DNN, a deep neural network with 20 units in the beginning and a ReLU activation function, 10 units as a second layer and a similar ReLU activation function, and a single dense with a linear activation function if you don't specify it by default, since we're doing a regression here. We're going to compile it with an MSE loss and SGD or learning rate of 10 to the minus 7. We have about 800 parameters fitted for 100 epochs. And we are predicting from time step 3000 and forward. So we see we're pretty close. The orange is the predicted value, and the blue one is the validation data set, which we aim to be as close as possible to. And we get an MAE of about 14.9. So the other network architecture we tried was combining a convolutional 1D, which we saw gave us better results from the previous few slides, and combining that with a 2-layer single directional LSTM and a DNN at the end of it. We apply a scaling factor here. We do the learning rate scheduler as we've seen before. We now jump to 60,000 parameters, 100 epochs. The loss versus learning rate seems a little bit stable for most of different values of learning rates. The more to the right, the better, or the lower loss it seems. So we picked 10 to the -5 in this case. Window size of 60, and Lawrence actually experimented with this a lot. Like, this was a good hyperparameter tuning session where he experimented with different filters, different window sizes, different batches, and also different values for LSTMs and dense networks. So the same, about 60,000 parameters, and we're now at 15.1, a little bit better. And if you plot the numbers, actually in the course, Lawrence looks at the numbers and he actually compares a specific number with the predicted value. He does some more hyperparameter tuning, and then based on that, he gets closer and closer to the actual predicted value for a given month. I found that interesting that he was going through that process. If you look at the loss, it's monotonically decreasing here. And we just have the loss plot. We don't have any MA or MSC on top of it. Cool. Any questions about this? To me, this seems like an application of all we learned, and can really tell if you're using real data or synthetic data. Our framework was about the same, and it was relatively an easy jump for us to go from where we were to here, given the really good build out that we had before, the really systematic approach. Okay.
So I mean, one observation just in general across the ways is that we're always good at kind of predicting the average, right? As long as we don't have extrapolate, as long as it stays within the range that we trained on. But we, we don't get that bias that goes in there, right? To find, from year to year, we can be off by quite a lot.
Mm-hmm.
Although across, several months, we're pretty close to the average across those months. But you see what I'm saying? Like,
yeah. So maybe one thing we should do to our data is, as a pre-processing step, is to identify if there's a trend, right? And somehow
filter it out
or remove it or change the scale. Instead of actual values, maybe you, let's say it's a stock, maybe instead of actual values, you do percent. But even then you might have out of bound or unseen range values.
Right.
And that's,
yeah, if anything, it looks like this particular sample here is over predicting a little bit.
oh, sorry.
The orange is often above the blue.
It's often above, yeah.
Except for the peaks, right? For the peaks, you're always under predicting.
Yeah.
But also what I find interesting is the trend was, it's kind of to tell because you also have peaks and impulses every now and then, but the lower values are pretty close to zero for several months. Like, the lower bound is pretty consistent.
Right.
It's not like it's deviating.
Oh yeah, that was one thing I was thinking about. I think a model that would probably work, well, I don't know, I'm guessing that it might work better to log transform this data before trying to fit it.
Right.
So yeah, that wouldn't impact your lower bound, but that would kind of scale your upper bound values.
But maybe the overall would look a little bit more sinusoidal if it were log transformed first.
Yeah, maybe we can try it, I'm not sure. Great.
You might end up with noise on the lower end, though.
Add more noise on the lower end, you said?
Maybe. I don't think the numbers are that low, though.
I mean, in many cases, it's almost close to zero. In other cases, it's just zero.
This is what average number of sunspots per day
per month. So one data point is actually 30 days.
But the values are not integers, so it's
average. Yeah.
The average. It's an integer value every day, and then divided by the number of days in the month.
I think so. So if you look at the actual table.
Oh yeah, must be.
Yeah.
Wait, is that our forecast, or is that the actual values?
It says forecast.
Forecast.
Yeah. So yeah. I mean, our values are going to be floats.
I think the values. I don't recall. I thought the values were floats also, though.
Yeah, they were. So if you go to the beginning, they were floats. Monthly,
so
yeah.
It's a mean, monthly mean. Yeah. Okay.
Yeah, monthly mean total sunspot number. There's a Wikipedia link there. If you want to take a deeper dive.
Okay.
So float in, float out. Cool. Some other
quick question, if I may ask.
Okay.
What was the width of a window that was considered for training at each step, and what percentage of that real data set was used for training? Was it 80%, 50%, or you took like the largest period and used it for training?
Doing all training, and he's using 60 months as the window.
So up to 3,000. So from 0 up to 3,000 was used for training.
Yes, I think so.
That's right.
And like if you were to take it, say from, I'm trying to find, since you said it's there are periods. So if you were to take it from say 1,000 up to 1, 2, 3,
For 11 years, yeah.
2,500, yeah. Like find some number of periods with peaks, not the whole thing, and see whether it makes a difference. So that's one question. And the other one is to make a prediction, how many steps do you go back to? Like how many data points do you take for each prediction step?
Yeah, so that's the
window size, yeah.
That's the window size, and we tried different ones. We tried 64, 60. We tried lower one in the beginning, and we noticed that if we increase it, we get slightly better results. Another thing is we were trying powers of 2 from other setups, but there's no need to stick with powers of 2.
So that's number of months, right?
Yeah.
64 months. So that's 5 years plus?
Yeah.
Okay. I mean,
yeah, I don't think you should read a whole period then, like a whole 11-year period.
I guess would sun's behavior be dependent on the way it was behaving, say, a year ago or even 5 years ago? I mean, I don't know enough physics about it to make a judgment, but you see the question I'm asking. I mean, are we picking the time window because it gives us better prediction, or it has some connection to physical phenomena?
Yeah, I think they're not picking the window based on physical phenomena at all. Just picking something that works for a toy problem. I think that's a really interesting parameter to play with, though, because if you happen to know the seasonality of your data, why wouldn't you try to leverage that somehow?
Yeah, and if you may remember the question I was asking you like last time, I was saying if you didn't plot the data the way you plotted it here, how would you pick like a starting point for training and the end point for training? So here, because you plotted data visually, you can kind of figure out visually what section you can take, and you don't even have to take it from the very beginning, right? And use that for training, like pick a nice subset, so to speak, and whether that gives you actually a better representation, right? Because the data that you have on the left side may be cut off.
I think it becomes a hyperparameter optimization problem if you're not able to, know the seasonality ahead of time. You've got to run it as, some kind of search over that window size. Mm-hmm.
Well, we're not trying to make like a perfect prediction. We're trying to like create a hypothesis, like figure out what's the physical problem we're solving, and then see whether we can come up with like general enough model, because it doesn't have to fit like 99% of time, right? At least it would be better than, say, deciding, going back 64 months works because it fits the data.
Yeah. Yeah, let's say you knew the period and somehow you use that to construct window size. I guess the question is, would you get better results or not?
Yeah, like for example, look, if you were to start from, let's say, a point 1000, and you finish training, you're training at the point, let me just take a guess, say 2000, right? About that much.
Mm-hmm.
So you capture enough periods. Would that be enough for you to, predict the rest? Does it capture enough? And likely yes. I mean, clearly there's something else that's, there's like more than one period here, right? Because the number of these spots oscillate.
Yeah.
It's not really like a sine function. Maybe it depends on some other planets or some other factors.
Yeah, that's what Lawrence mentioned in the course as well. You might have two periodicities or two seasonalities intertwined and give you this effect.
Yeah, he teased the question of whether it's a 100-year, or I'm sorry, 11-year cycle versus a 22-year cycle, and challenged us to answer that question, and I think none of us did.
It's fine. I mean, as a matter of fact, as you alluded to it, if you were just were to discard all the data points and just focus on the peaks, right, within certain range, and try to fit a line, then you would be able to see whether there are like some additional periods, right?
Yeah.
Thank you, guys.
Sure. Cool. So in terms of a few other data sets, and we will look at one more for the day. It's machinelearningmastery.com. It's a great website for machine learning resources. It has a GitHub repository with different data sets on binary classification, like credit card fraud, for example. Multi-class classification data sets, classifying wine, for example, or wheat seeds. It has several on univariate time series, for example, minimum or maximum temperature in a city. Sunspots was another one, car sales, and so forth. It has a regression data set on, like, for example, housing, or multivariate time series, so pollution, indoor movement, and so forth. From this data set, we're going to use this daily minimum temperature in Melbourne, Australia. And let's see how that data looks like. So I think the time scale here is days, and each value is the minimum temperature for that day. And I think the scale is in Celsius. So 0 means it's freezing, and 25 is that in the 70s, I guess, Fahrenheit. Guess
77.
Yeah, and you see the seasonality here. It goes from low to high, and let's see if we can figure it out. What is the seasonality? From 0 to 400 something. Is that a year? Looks like a year, 365 maybe. So this looks like a year of data, right? a year of data, another year of data, another year of data, another year of data. So the lower one is the winter for Australia or summer for us. It's they're in the southern hemisphere. And the peak values is summer for them and winter for us. If my memory serves me well.
So
yeah.
perhaps it starts on, yeah, I was going to say it starts on January 1st.
Probably, yeah. Yeah. So yeah, looking at the data always helps. January 1st, 1981, and January 2nd, January 3rd, and so forth. So splitting the data, yeah, we kind of suspect, or we kind of know that this data was suspected to be annually seasoned, have annual seasonality. So we picked a value. I'm not sure if this is an even number of years here, but it kind of looks like it is. And I'm not sure if this point, I think we had a discussion. I don't think this point, if you're a little bit to the left, a little bit to the right, makes a huge difference in your results. Like your model should still be able to predict somewhat accurately the next few years of values. So we stop at 2,500 and we're going to predict for about 1, 2, 3 more years of data. And we will use this combination of conv and LSTM and dense looks like it's giving us good results. We're going to set the window size to 60. Again, 60 days means 2 months. So we're taking about 2 months of data each time and running it through this network. We did, again, the minimum loss for different learning rates. We ended up with a value of 10 to the minus 5. We plug it back in. We train for 100 epochs. And when we forecast, we get something like this. Pretty noisy, as you can tell. And the MA we got was 1.8, which is not that bad. One thing to consider is this also is affected a little bit by the scale, I suspect. So our numbers go from 0 to 25 versus our previous examples where our values were much, much higher. Our range of values was much, much higher. And looking at the loss, it looks like we're still down training by a very, very small amount, 1.58 by 0.56. And we're making progress, even though by a little bit, epoch after epoch. That's all I had for this data set. Any questions about this specific data set and this specific model? Something I'm thinking about is, I don't know if maybe a hybrid approach, like usually when you're doing prediction for forecast, usually a hybrid approach of deep learning and statistical methods usually gives you better results. So maybe a smooth version of our forecast might give us a lower MA, a lower mean absolute layer, something to think about. Yep, our model has no idea about winter, summer, fall, spring, right? That's interesting. Cool. Great. Then if there are no more questions, again, a reminder that this is the last course, course 4, and we just covered week 3 and week 4 of TensorFlow and Practice Specialization. That actually concludes the entire specialization. And I want to thank everybody for being a part of this journey. It's been awesome. It's been amazing. I was looking at our very first few meetups and sessions where we're trying to figure out the structure of the meetup, how often should we meet, and what should we cover. All the way where we're now, we have a very well formatted, very well put together process, very good collaboration from all of us, especially from David and Robert. So I want to thank you everyone for joining us. If you've taken the specialization and completed it, congratulations. I hope you learned a lot, and thank you for joining us. I encourage you to join us next on our next session, July 3rd. We'll have Lawrence joining us and sharing his feedback and his input with us, but also it'd be nice if we as a community shared some of our comments, some of our feedback, what we learned, what we found interesting, back to him, so that he can also take it back to his team and probably enhance or tune their specialization over time. Then after that, on July 10th, we have a session on the TensorFlow Developer Certificate. Given the specialization and given the notebooks that we've worked on and different models we've worked on, we're in very good shape to take this certificate and actually pass it. So I will cover that on July 10th. Questions, comments, feedback about these upcoming sessions?
Thank you very much for all your hard work on this.
Yeah, absolutely. Yeah. Please join us and share about our next upcoming session. I want to make sure we have a good turn up, Lawrence.
Yep.
And I added one more slides here about some other forecasting content. One of them is that paper that I mentioned. There was an event that introduced it about this tuning of your learning rate, where you start with a smaller learning rate, you increase it, and then you decrease it. This is the paper that introduced it. I also wanted to mention quickly this competition of forecasting. It's actually the 5th version of it, that you have different data sets, about time series data sets, 10,000 time series of yearly, quarterly, monthly, weekly, daily, or even hourly. And the goal is to create models that predict relatively well in different time scales. And I have another screenshot here from Uber. Uber also introduced their own hybrid model that was based on a statistical approach and also deep learning model that I think performed relatively well.
I have a, I'm audible?
Yeah, we can hear you.
Yes.
Yeah. I have just might be a very basic question. Like looking into this time series data, right? We have a timestamp and then there is a temperature for suppose 1 year. Do we feel a deep learning model is really needed for that? Because normally deep learning model is needed for non-linearity and extracting features and all. So might be a normal machine learning regressor will solve the problem. We need to go for a LSTM, bidirectional LSTM, this type of robust network to solve this type of problem?
Yeah, I think that's a great question, and our results from the last course show that the more complicated models we tried to throw at this problem didn't really do all that well. I suspect that in many cases it would be much more effective and obviously less costly to try much simpler approaches, such as autoregressive or ARIMA models.
Yep. Okay. Yeah. Thanks.
Sure. Thank you, Robert. Another thing that I wanted to mention is many of us use Colab. Colab actually has a pro version. Colab by default is free, but the pro version for $10 a month, you get a faster GPU, and you also get longer runtimes and a little bit more memory. So if you think that your models take more than 12 hours is the maximum time that Colab allows you to run something, and then it will disconnect you. I think this one allows you for 24 hours. Yeah, check it out. It's a great resource, and it runs on the cloud. You can run it from any computer. You don't have to have anything on your end. The TensorFlow tutorial section also is very interesting, and I encourage us to take a look at different applications. It has applications on NLP, on image, on even structured data that we plan to cover in the future. So it is a very interesting tutorial, and it has different aspects of using TensorFlow from the beginner to advanced level. A few specializations that few of us I have heard have taken or are taking is healthcare related. One of them is from Coursera, this AI for medicine specialization, and another one from Udacity. AI for healthcare. So if there's something that you're interested in, go check it out and let us know what you think, and maybe sometime in the future we can tackle them. That'd be interesting. Yeah, the developer certificate that I mentioned before, the deep learning with Python book. I think it's available on discounted price for about, I think, $23 online. The first 6 chapters I've been reading for version 2 or edition 2 of this book. Francois is the developer of Keras, the original developer. And this book I recommend because when I was trying to understand sequential models and RNN and STM better, I found this approach of decomposing what happens within a model very interesting. It was basically looking at the input, it was looking at the weights at different layers, and it was doing all the mathematical calculations that you see that you have seen. It was actually combining them, and it was doing them step by step. It's kind of like doing your own neural network from scratch, but it was using the model and layers from a Keras model. I like that approach here. Cool. With that said, we won't have time for quiz, but I posted quiz 5. It has content for everything we've learned on forecasting. And if you're new to this is a fun, engaging way for you to practice concept, also have fun and see how many questions you can get right and validate your knowledge. So with that, I want to thank everybody. Thanks for joining us. It's been a fun experience, and hope to see you next time with Lawrence.
Thank you.
Yeah, thank you, George.
Thank you, everyone.
Thank you, everyone.
Have a great night.